All right, as for today, we're going to talk about chi-squared, which is very similar to things that we have been looking at. It's still proportions, but now actually our proportions are many distributions instead of just one or two. So a simple example here. Does your zodiac sign determine how successful you will be later in life? Fortune magazine collected the zodiac signs of 256 heads of the 400 largest companies. The number of births for each sign is listed in the table below here. And we can see some variation, all right? Like we see that there are more Pisces. But is that enough to claim that successful people are more likely born under one sign than another? So we have 12 zodiac signs. And so basically we're identifying each of those proportions. P1 equals P2, which equals P3, equals P12. All right. We are saying that all 12 of these proportions are the same, or at least one PI is different. And so this is very, very similar to our hypotheses that we had before. All right, a bunch of proportions are equal or something is different. Now, we don't have the same situation that, oh, this one is greater than this one, this is greater than this one. All right, we are just going to test there's all the same or something is different. Now, because it's also a pain to write this out, most of the time we write this, all right, completely in words. This test is known as the goodness of fit test. The proportions are all right, equal to 12, all right? 1/12, all right? Or something is different. And typically we just write these as the probabilities are the same or they are different. So we even write these hypotheses in words. And this helps with our conclusions because if you write good hypotheses, usually what we do in our conclusions is we interpret our hypotheses into context. But basically from the beginning now, we are going to write our hypotheses completely, all right, in context. And there are multiple ways to do this. Zodiac birth rates have equal probabilities, the same probabilities, or even distribution, some synonym for same, all right? And then the alternative is zodiac birth rates do not have equal probabilities, do not have same probabilities, or are unevenly distributed. Our conditions, which is always something we check, finally are going to change. We no longer have the assumption the distribution is normal because now we have a chi-squared distribution. That means our conditions are slightly changing. The large enough condition, n greater than or equal to 30, is no longer going to be here. We now have what is known as the cell count condition, which is the expected cell count is greater than or equal to 5. So sort of like the success failure condition. There's also the cell independence condition and the randomization condition. Now be aware, these conditions we have been inherently checking all along. We just never officially check them. You just kind of think, all right, as long as this data was randomly collected, I should be okay. The only one we're fully going to check is the cell count condition. So this is our new condition, and that's what we're going to be checking from here on. And in order to check that, we actually need to use StatCrunch because the expected cell counts is actually what StatCrunch gives us. This one, all right, and that's what we had here. I can identify this approximately, and I'll show how to get this in StatCrunch because the more complicated it gets, you want to have StatCrunch do the calculation for you. If we have 12 zodiac signs, that means each one has a 1 in 12 probability. There are 256 data values because we collected the 256 head CEOs of these companies, which means my expected cell count is 256 divided by 12, aka 21.3. That means if these were evenly distributed, each of these values would say 21.3. And basically looking at the numbers, all these numbers, 23, 21.3, 20, 21.3, we can see they're all pretty close to 21.3. Because that's, if it was completely random, that's what we would expect if the probabilities are even. And we see, right, Pisces down here, that one is the biggest distance, 21.3 versus 29. Now again, StatCrunch is going to do the calculation to see, is that big enough, right? Is that value big enough, or is that just sampling variability? So our cell count condition, the expected cell count is 21.3. That is greater than or equal to 5. And that is our singular condition. So the condition is met. We may assume the sampling distribution is chi-squared. And again, not normal, chi-squared. All right, so we have a different distribution now. We have a new test statistic, the chi-squared test statistic, all right? So we now have Z, T, and chi-squared. And the calculation, although again, not difficult, each observation minus the expected value squared divided by the expected value, sum them all up. StatCrunch is going to take care of that for us, all right? And we're going to look at that in just 2 seconds. So StatCrunch, goodness fit, chi-squared test. All right, so here's our Zodiac data set. All right, so we have our Zodiac data set, stat, and goodness of fit is down here. Chi-squared. We select births and all cells in equal proportion. So there is one where you can select a column and we compare it to particular values, but most of the time, equal, unequal. And then, okay, display. Okay, and everything is good. And our output. And so here's the expected value. So this one was simple enough where we were able to calculate that by hand, because 256 divided by 12 is super easy. But StatCrunch always gives it to us. So basically, I just look at these values and are these all greater than 5? Yep. Since they're all greater than 5, then our condition is met. And then we, just like always, I have my chi-squared value, all right, and my p-value. So here's my new test statistic, 5.09, and p-value, which we've been doing all along, is 0.93. And I put the output in here just so we have it. But those are the 2 values that we're actually looking for. And then as always, conclusions, the best part. So with a p-value of 0.93, reject or fail to reject.
Fail to reject.
Fail to reject, right? That's high. All right. So fail to reject HO at a 5% significance level. There is weak evidence to show that. And then here's the best part. Because our hypotheses, all right, we wrote them in words. That means you literally, if you did a good job on your hypotheses, then you have those hypotheses, all right, already explained in context. There is weak evidence to show that zodiac birth rates are unevenly distributed. And that's it. I was like, again, check our conditions, write our hypotheses, StatCrunch conclusions. The process is very, very simple. The trick of these is going to come in that there are 3 different chi-squared tests. So the test of goodness of fit is the first one. And basically that is one-dimensional data. That is always going to be a line of data. The other 2, the test of homogeneity and the test of independence, is when we have 2-dimensional data. The only way to identify the difference between these 2 is the test of homogeneity is an extension of the test of goodness of fit. It identifies, are these things the same or are these things different? Which is exactly what it looks like in the hypotheses. The distribution of whatever is the same for all categories, or the distribution of whatever is different for the categories. For the chi-squared test of independence, all right, which is something we've actually done quite a bit, determining if 2 things are independent or dependent, we want to see, all right, if the 2 things are related, associated, connected. Is there a relationship? Are they independent? Are they dependent? And so it is only the wording of the question that will separate these 2 categories, these 2 chi-square tests. Our hypotheses are exactly what we would expect as well, though. The 2 variables are independent or the 2 variables are dependent. Now, good news, the conditions are the same for all chi-squared tests. The only one we have to check is the cell count condition. We check the cell counts, which basically we look at StatCrunch. And then if it's greater than or equal to 5, we're good. If not, we stop, right? Conditions failing, that's the big one. And so this is the big thing, all right? Homogeneity versus independence, all right? Both homogeneity and independence, all right, used chi-squared test, and it is calculated the same way. The difference is identifying within the wording. So homogeneity will say things like same, equal, even, right? And then vice versa, different, unequal, and uneven. Chi-squared tests of independence, it will say associated, dependent, related, and then in reverse, independent and unrelated. There isn't really a word for unassociated, but it's only in the wording of the question, what question is being asked specifically, all right? The wording of the question regarding what we're looking for. Are these two variables connected or are these two variables the same? All right, and that is really the only difference. Condition-wise, calculation-wise, p-value, those are all exactly identical. But the question being asked is all about the context that is being presented. All right, so this is a big wording part. All right, so in StatCrunch, and then I'll show you what we need to select, and it's all right there. So let's look at an example and identify which one we're doing. All right, so we have the chi-squared test of goodness of fit, chi-squared test of homogeneity, chi-squared test of independence. I know this is not the chi-squared test of goodness of fit. Okay, this is definitely not the chi-squared test of goodness of fit because I have two-dimensional data. All right, it has both rows and columns. Goodness of fit would only have one row. Okay, so I know it's not that one. That means this is either the chi-squared test of homogeneity or the chi-squared test of independence. And I can identify that part without even reading the setup, just by looking at the table. Okay? Okay, so now let's read and let's see what's going on. Many universities survey graduating classes to determine the plans of the graduates. We might wonder whether the plans of the students are the same at different departments within a university. The following two-way table has post-graduation activities for a recent graduating class at a large university. The data set is located in post-grad plans. So there's a key word in here.
Same.
Good job. Same. Okay. Might wonder whether the plans of the students are the same, all right, at the different departments. Okay, that different doesn't mean anything, right? That's just distinguishing between ag and engineering, etc. So it's that word same. That means this is the chi-squared test of homogeneity. And so, all right, that means now I have the ability to write my hypotheses. All right, so now back to context, the post-grad plans of students are the same for all 4 departments. And then the alternative would be, all right, the post-grad plans, all right, of students are different for at least one department. Now, be aware, the post-grad plans for 3 of the departments could be the same, and one of them is different, or all 4 could be different. So that statement is saying that at least one of them is different, all right? Could be 2 of them, could be 3 of them, could be all 4, all right? And we write these in a general way that all the same, something different. That's all this is saying. All right, so our condition. And again, condition singular. The expected value. And basically, the best thing to do here is actually find the lowest, the smallest expected value. Because basically, if I identify the smallest expected value and it's over 5, then all the rest are. And we're about to see that all these values are going to be different. It's not like we saw before where they were all 21.3. Okay, so postgrad. Okay, so here's our post-grad plans data set. Stat, tables, contingency. And that should be familiar. We've been doing contingency tables since we initially started, right? That was the Titanic data set we looked at way in the beginning. And we have, this is with summary. Okay, this is not data. All right, so select my columns, which is all 4 of those. And plan. And then we need to make sure we display the expected count. We've actually come here before, all right? We've looked at this and we got the row percent and the column percent of total, all right? And this is what you were doing on your project too, all right? So actually, this does look familiar, right?
Yeah.
But now the only thing we need is the expected count, because that's going to help us check our conditions. So I see the expected counts are the ones in parentheses. All right, 200, 200, 140s, And so basically I'm looking for the smallest of these. And it's right here. Now notice the counts are actually smaller, okay? So it's possible the counts are below this value, counts are above this value. But basically the smallest one is 32.77. Is that greater than 5? Yeah. So the smallest one is, I already forgot what the number was, 32.77. Which is greater than or equal to 5. The condition is met. We may assume the sampling distribution is chi-squared. Now, something else to note here. Okay, so we have here's our test statistic. The value is 106.45 and the p-value is 0. Notice what this does not have that all our other output does have. There's no hypotheses here. Okay? StatCrunch doesn't present your hypotheses, right? When we've been doing the means and the proportions, 1 sample and 2 sample, remember it shows your hypotheses so you can kind of compare what you have written to what's on StatCrunch. It doesn't do that. It assumes you know what you're doing. And it's because it's dependent upon the context, right? Homogeneity and test of independence have the exact same calculation. It's all about the context. So you can't compare your hypotheses like we have been doing in the past. Okay, 106.45. Reject or fail to reject HO?
Reject,
You sure?
fail to reject. Right? Yeah, fail to reject.
Our p-value is 0. Significance level 5% is 0 less than 5. So what do we do?
Reject.
Reject. All right, always write the rule, right? If you need the rule, always write the rule. But this is the lowest value it can be, right? If P is low, the HO must go, right? All right, and remember with reject HO, strong evidence, fail to reject HO, weak evidence. Remember, these words are always paired with your decision. And here's the best part. So there is strong evidence to show that. I mean, that's kind of our generic statement. The context, we already did it. It's right here. All I have to do, if you do a good job in your hypotheses, your conclusion is basically written for you. There is strong evidence to show that the post-grad plans of students are different for at least one department. And so, all right, the post-grad plans of students are different for at least one department. That is literally exactly what I had written in my alternative hypothesis. Writing your hypotheses in words from the beginning is always an acceptable practice. You can write the whole thing in words. Why do we use the notation? Because it's way shorter, right? And we don't worry about interpreting until the end. This way, if we write in the notation, actually that's worse. That's longer than writing it, all right, in just context. So practicing context from the start to the finish of all these problems is the best practice. All right, let's look at another one. Is this a chi-squared goodness of fit test?
Mm,
No. Once again, because I have 2 dimensions of data, all right? Just seeing the data, I know this is not the chi-squared goodness fit. That means this is either a test of independence or a test of homogeneity. All right, so a study from a large university examined 626 people being treated for non-blood related diseases to see whether the risk of hepatitis C was related to whether people had tattoos and to where they got their tattoos. Conduct an appropriate hypothesis test. The data set is located StatCrunch tattoo Hep C table. Is there a key word in here that tells me which is which? What word? Related. Again, there are no, I mean, I literally wrote every synonym we have. Related, associated, dependent, right? Same, different, even. Those are basically the only words that you can use, all right, to say, to distinguish between these two tests. So chi-squared test of independence. Actually, we should note one other thing. So notice that the very first thing I'm doing is identifying what type of problem. Notice what I'm not doing. Identifying all our information. Because we don't really have any to identify anymore. We don't have means or proportions or any of that to identify. The important part is identifying what test you're in. So my identification is this part. Reading the problem and then knowing which of the three tests I need to do. Okay, let's see. So our two variables are Hep C status. So Hep C status and tattoo location. That's actually because it's parlor, elsewhere none. Tattoo, actually tattoo status. I don't see how else to say that. So Hep C status and tattoo status are independent variables. Versus Hep C status and tattoo status are dependent variables. All right. So for our conditions to StatCrunch, we go. Tattoo Hep C table, and it's same as before. Stat tables, contingency with summary again. And my columns were Hep C, no Hep C. Location are my row variables, and I need my display expected count. How does this look?
That's the 4.58, right?
Is that the lowest one?
Oh, no, 3.9.
Ah. Notice down here. Warning, over 20% of cells have an expected cell count less than 5. Chi-square suspect. StatCrunch actually says, whoa, whoa, whoa. All right. This is problematic. All right. So it's actually telling you that conditions fail. Now, be aware, it actually only does this when 20%, but basically you look for your lowest one. But if lots of them are low, like in this, 2 out of 6, all right, StatCrunch even says be careful. All right, but already, so I see, okay, so we're going to grab 3.9, the smallest value. Is that greater than 5?
No.
No. So less than 5, the condition fails. We cannot assume the sampling distribution is chi-squared. And what do we do?
Fail to reject.
Oh, no,
Oh, wait.
stop,
Oh, stop a little bit.
right? We didn't even get to our test statistic and decisions, all right? Because our condition failed, which means we stop. All right, and that's the big part. You want your conditions to fail, right? Because look, we're done. Okay, so that's the big thing. Always check your conditions and be thorough. All right. So along those lines, looking at that one we just looked at. So note our condition, right? Our cell count condition, all right, it failed. So a common thing is actually to go through and combine cells. And this is what you did in your project, right? When you have all these small cells, well, combine them. And specifically, the two conditions that failed, the two cells that failed were the tattoo parlor elsewhere, parlor and elsewhere. These two cell counts failed. So combine those. So 17 plus 8. Oh, that becomes 25. And basically I combined those two top rows and I could reconduct this test. And this would be appropriate because I'm going to bet the cell count condition passes here. So that's the biggest thing. All right. You want to be careful. All right. When your conditions fail, we don't just have to stop. We can, all right, move forward. We can combine cells and move forward. Also, be careful of our conclusions. Remember that we are saying that these two things are independent or dependent. We're not saying that do tattoos cause Hep C? No. I mean, we're not saying that. Okay, we're saying that there isn't a relationship between Hep C and having a tattoo. But it's not that tattoos cause Hep C. Okay, there's an underlying variable there, right? Needles, blood, that's what transmits the disease. All right. And then watch out for large sample sizes, because if you get a big enough sample size, you'll always reject HO. All right. But mostly we're not going to have to worry about that too much for our purposes. Also, notice that's basically the end of the lecture. Did we do any confidence intervals? No. Chi-squared is only hypothesis testing. So once you identify you're doing chi-squared tests, that should only be hypotheses. All right. No confidence intervals, no sample size calculations. All right. That wasn't too bad, huh? That's good stuff.
Yeah. So on the